Hey there, people. Today we are talking about section 6.4, the fundamental theorem of calculus. So yes, this is kind of important. So we're going to learn about part 1 and part 2, graphing our functions, connecting it to area, and then analyzing our antiderivatives graphically. So we're going to start with the fundamental theorem of calculus. If f is continuous on a to b, then the function, notice that this is a capital F here, so capital F, and so this is the antiderivative or the integral of little f. It has a derivative at every point on a to b, and you can find the antiderivative or the derivative of the integral. You're gonna take this top value and substitute it in place of t. So we just ended up with f of x. So again, this is the same thing that was on the last page. Every continuous function f is a derivative of some other function, and every continuous function has an antiderivative. The process of integration and differentiation are inverses of one another. So that's kind of like squaring something and taking the square root, or multiplying by 4 or dividing by 4, okay? Inverse functions, integrating and taking the derivative are inverse functions of each other. So we are going to do this. First thing here, our variable is x, so we're going to substitute it in right there. And we end up with sine of x. Done with that one. This one works a little bit differently. So on this one here, we're substituting our x squared in there. But because this isn't just an x up here, we also need to multiply by the derivative of that. So we get this. And it doesn't matter what your lower bounds is. Honestly, if we go back to this last page here, see if I can click it. That was pi. This one starts at 1. The lower bounds doesn't really matter, okay? Unless it's a different variable, then it will matter. But for this one, it's not going to matter. All right, this guy here is kind of flipped around from what we saw. So we are going to find the derivative of this function. And I am actually going to flip this around so the top value is x. And because I did that, oops, there we go. Because I flipped these around, notice that x was on the bottom, 5 was on the top. I get a negative in the front. That's just a negative area. So I am substituting x in. And this is my value. All right, so we are going to do some of these in class. I am not doing them with you. If you want to try them prior, that would be great. If not, you're going to have a little bit more work to do in class that the rest of us won't. All right, fundamental theorem of calculus part 2 says if f is continuous at every point from a to b, and capital F is any antiderivative of f on a to b, then your integral from a to b of f of x dx is equal to f of b minus f of a. So basically, we're just filling these values in to find out the difference between them, okay? It's the integral evaluation theorem, but really this is, I mean, we use this one most often, okay? So any definite integral of any continuous function f can be calculated without taking limits, without calculating Riemann sums, and often without effort, so long as an antiderivative of f can be found. So antiderivatives, we have started, but the more you do, the better you'll get. We're going to do this one as an antiderivative. So I am starting by looking at 3x squared. So usually when we're finding the derivative, we drop our exponent down and subtract 1. So I am going to start by adding 1 to my exponent. And then I had that 3 in the front here. But then I need to divide, I multiply by the reciprocal, whatever your exponent is. Okay, so it's 1/3. I will simplify this in just a minute. I'm going up, x comes from, like if you find the derivative of x, we get 1. All right, and we are going to do that from -1 to 3. Boom, boom, boom. These guys simplify. I'm just going to kind of leave it like this. So basically what I'm doing is it's always upper limit substituted in minus the lower limit substituted in. Oh, this is fun. The pen just erased. Okay, so I am substituting 3 in. And then I am going to subtract -1 substituted in. And I'm going to find these values. So 27 plus 3. And I'm subtracting -1 minus 1. So I have 30 plus 2 equals 32. And that is it for the fundamental theorem of calculus part 2. So how do we find the total area analytically? So to find them between the graph of f of x and the x-axis, you are going to partition a to b with the zeros. And why do we do that? Because if you have, that wasn't straight at all, if you have some function that has values above and below the axis, okay, what you want to do is divide them, find the area of each piece, integrate each piece, and then add them as absolute values because we want total area. Total area. So how much area is here, how much area is here, how much area is there, that's the total area. Okay, it would be the same as total distance versus where did I start and where did I end. This would be total distance. How far did I travel total? So I went forward this amount, I went backwards this amount, and I went back forward. How much did I travel total? To find it numerically, you can just nint it. When in doubt, nint it out. You can put this in your calculator with the absolute value sign. And absolute value is math. And then let me pull your calculator out. It's math, go over to number. So hit the over arrow, go over to number, and it should be number 1. It says ABS. Yep, with a parentheses. It should come up as an actual absolute value sign in your calculator. And then do these by hand and then check in your calculator. So we will do these in class, okay? But I want you to have them ready so we can go through them. And that is it for today's lesson.